Dear students, in this video on current electricity, we will study about meter bridge, potentiometer and numerical problems based on them. So let us begin with meter bridge. It consists of a 1 meter long resistance wire and it works on the principle of balanced Wheatstonebridge. So here we have all the arms of a Wheatstonebridge and all the resistances are connected through copper strips. So you can see we have a resistance box as resistance P, unknown resistance Q, and we have a galvanometer connected as the middle arm, and the resistance is connected to a cell through a resistance. The free end of the galvanometer is connected to jockey. This jockey can slide over this resistance. Now the jockey divides the resistance wire in two parts. One is R, the other one is S. So we have got the four arms of a Wheatstonebridge: P, Q, R, S, the middle arm of galvanometer also, right? The current starts from this cell, divides at these parts and finally returns back to the cell. Okay, now if one part of the resistance wire is L, the other part will be 100 minus L centimeter, right? So we have got all the parts of a balanced Wheatstonebridge rather. Now when no current passes through galvanometer or when it is not showing any deflection, we say that this position is a null deflection position, and in that case we will get P upon Q is equal to R upon S. Now resistance of any wire is directly proportional to its length, so R is proportional to L. Similarly, S is proportional to 100 minus L, right? So using all these things we can find out an unknown resistance and its resistivity also. Okay, so let's see how we do it. So to find unknown resistance and resistivity, see, in null deflection position, when no current passes through the galvanometer, you get P upon Q is equal to R upon S, the condition for balanced Wheatstonebridge. Now resistance is proportional to its length of the wire, so R is proportional to L, S is proportional to 100 minus L. In this way we get this relation. So unknown resistance Q is equal to P into 100 minus L upon L, just rearranging the equation. And then you have this relation, resistivity rho is equal to R A upon L. So A is area of cross section, L is length of the unknown resistance, Q is its resistance that we have just calculated, and we can measure the diameter or radius of the unknown resistance. We can measure its length. So putting all these values in this equation, we can calculate the resistivity of the unknown resistance. Okay. Now, an important point to note: the null deflection position must be obtained near the middle of the bridge to reduce percentage error. You see, we have got a resistance box, so we adjust resistances in such a way that we obtain null deflection position between 40 and 60 centimeter, and if we do so, the percentage error is reduced. The resistances in all four arms must be comparable. So now let us move on to potentiometer, and as the name suggests, this instrument is used to measure potential difference between any 2 points. So its principle. Now when a steady current passes through a resistance of uniform cross-sectional area and uniform composition, then the potential difference across any segment will be directly proportional to its length. That means when we have any resistance wire, say AB, and a constant current is passing through it, then the potential difference across its length will be directly proportional to its length. That is the principle, and it is very easy to understand using this Ohm's law. See, the potential difference across this resistance wire is equal to IR, and R can be written as rho L upon A. Right? Now just rearranging the terms, I can write rho I upon A. Now rho is constant for the given resistance wire, it is resistivity. I is constant because the current is constant, it is steady current, and area of cross section is also constant for a given resistance wire, and we are talking about uniform composition and uniform cross sectional area, right? So we can say that this V is proportional to L, or potential difference is proportional to the length of the wire. If the length of the wire increases, potential difference will also increase. If the length of the wire is decreased, potential difference will also decrease. Now, using a constant, we can write V is equal to KL. Now, this constant K is called potential gradient. You see how we define this potential gradient? It is the rate of fall of potential along the length of a current carrying conductor. You can see that this K is equal to V upon L. So this is fall of potential upon length. See, this point is at higher potential, this point is at lower potential. Current flows from higher potential to lower potential, and with length the potential will go on falling. So it is rate of fall of potential with the length of the wire, and its SI unit will be V upon L, that is volt per meter. Volt per meter. This is the SI unit of potential gradient, और वोल्ट पर मीटर पोटेंशियल SI यूनिट होती है इलेक्ट्रिक फील्ड की भी. I hope you remember that. So let us look at the construction and working of a potentiometer. So here again we have a long resistance wire AB, which is connected to a driver battery. You can look at this diagram. This battery gives current to this resistance wire AB, also called potentiometer wire, and a cell is connected to this resistance wire along with a galvanometer, and the free end of the galvanometer is connected through a jockey. So let us see what happens. Now, as soon as this end is connected to this resistance wire AB, circuit is completed, and current starts from this driver battery here, and current starts from the cell also. See, at this point A, you can see opposite currents. The cell E and E dash are sending currents in opposite directions. So let's see what we get now. Now, at point A, these two currents will combine. We can use junction rule here. So these two currents combine and their sum will pass along AJ. So let the current from the driver battery be I1 and current from the cell be I2. Okay. So current along AJ is equal to I1 plus I2. Okay. Now the moment the moment the current reaches at this junction J, the current I2 is returned back to the cell, and in galvanometer the current is entering like this, right? So remaining current will pass through the JB part. Okay, so look at it. See, I2 is returned back to the cell E and I1 is returning back to the driver battery. So I hope this circuit is very clear to you, that from driver battery we are getting current I1 and from this cell we are getting current I2. At this point they both are combining together to give I1 plus I2. At this end of the jockey, this I2 current is returned back to the cell and I1 current goes back uh, along this path to the battery. Now, what is the possibility of this kind of flow of current? So, this is possible only and only when, you see, this driver battery has greater EMF than this cell, necessary condition. And the potential difference between A and J, this potential difference from here till this point J, is lesser than this EMF of the cell. So if you look at just this part of it, forget about everything else. If this E is greater, its current will dominate the circuit. So current will start from here and this potential difference is there. So the direction of flow of current is going to be like this, as you can understand. So this kind of flow is possible when the EMF of this cell is greater than this potential difference. Okay, I hope you understand it. Now, another possible situation, the same circuit, but here we are taking different situation. See, now here what is happening is, we will take the potential difference between A and J, this potential difference, as greater than E. So let's see what we get. Look at it. The current is coming from driver cell and current is going into this cell. Just the opposite. In the previous case, current is coming out of it. So, further. Current I1 from driver cell and current I2 is entering the smaller cell, and you can see here this I1 is coming here, I2 goes to this part, and the remaining current I1 minus I2 will pass along this direction, right? And this I2 will move this way through the galvanometer, and I2 is leaving galvanometer, and at this point I2 will meet I1 minus I2 and then they will combine together to give I1 here. I hope you understand it. Let's look at it. So you can see the path taken by the I2 current and path taken by I1, and then I1 minus I2, and then finally I1 is returned back to the cell. So it's very important to understand this working, that I1 current is starting from here, right? One part I2 goes here, the remaining part goes this way. This I2 takes full path and at this point it is meeting it, and then combining, I1 goes back to the cell. Now see, in the previous case current was entering the galvanometer in this way, and in this case current is moving along this way. So the galvanometer will give opposite deflections. In the previous case, if the deflection was like this, in this case the deflection will be like this, opposite deflections, right? Now between these two opposite deflections we can obtain a situation. Just look at it. See, this is possible only and only when this VAJ is greater than this cell. VAJ is the dominating factor here. Okay? You can see that if this potential is more, current will pass through this way along this path. You're familiar with it. So as I was telling you, Between these opposite deflections, there will be a situation when the potential difference between A and J will be same as that of the EMF of the cell, and in that case no current will be drawn from the cell. Just look at it here. See, current I1 is drawn from the battery, driver battery, you see, but no current is passing through this E, and you can see that here I1 is coming from here and I2 is 0, so full I1 is going along this path, and there is no current here, no current here, so I1 is coming and I1 is following just this path, as if this does not exist. And this is possible only when this potential difference between A and J is equal to the potential difference of this EMF, and in that case no current will pass through this segment. Okay, so you can see the path followed by the current. See, this situation is called null deflection situation. See, this is necessary condition. E dash should always be greater than E. If it is not so, we will never obtain this null deflection position. So EMF of driver battery must be greater than EMF of the cell. Another necessary condition is the positive terminal of the battery and positive terminal of the cell must be connected to the same terminal of the potentiometer wire. If we do not do so, we will not obtain opposing currents, and then null deflection position will not be possible. Okay, so this is called null deflection position or balance position, right? And now, how do we use this potentiometer in circuits? So its first use is to compare EMFs of two primary cells. So here your driver battery and the potentiometer wire AB. Now we have two cells connected in parallel to this potentiometer wire. You can see we have two primary cells E1 and E2. They are connected in parallel to this parallel to each other, and to their positive terminals are connected to the one terminal of potentiometer wire, and the same terminal is connected to the this terminal of potentiometer wire, so that they can give opposing currents. Now the other ends of the cell are connected to a two-way key, and through a resistance a galvanometer is connected, and then we have a jockey which is free to move over this wire AB, potentiometer wire AB. Now the current from driver battery starts I, and see, in null deflection position no current will be drawn from either of the cell. Okay, so look at it. Now what is the role of this two-way key? What we can do is we can put cells in the circuit one by one. Means जब हम E1 को सेल में सर्किट में डालेंगे तो E2 हमारा ऑफ रहेगा, और जब E2 को सर्किट में डालेंगे तो E1 को हम ओपन कर देंगे या ऑफ कर देंगे. So that is the role of this two-way key. Okay, so I hope the circuit is clear. Okay, so now how do we calculate the values? See, when cell E1 is in closed circuit and E2 is in open circuit and the balancing length is L1, then clearly E1 is proportional to L1. See, we have done the principle that V is proportional to L, potential drop. Now when cell E1 is in open circuit and E2 is in closed circuit, the balancing length is L2, then E2 is proportional to L2. And dividing this equation by this equation, you get E1 upon E2 is equal to L1 upon L2. And you can measure L1 and L2, and by measuring L1 and L2, we can compare EMFs of two cells. Now you have to perform this experiment in laboratory. Now the next experiment. To find internal resistance of a primary cell. See how we do it. See, the basic driver circuit does not change at all. The role of this driver battery is to provide current to the potentiometer wire. You can see it provides current to the potentiometer wire, and it provides potential gradient to this wire. Potential gradient is important here. So it provides potential difference as well as potential gradient. So now we want to find out internal resistance of a cell. Here in parallel to the cell, we connect a resistance box, a key, and through a resistance it is connected to a galvanometer, and through a jockey it can slide over this potentiometer wire. Now see what happens. First we keep this key open. Now when this key is open, this resistance box is not in the circuit, right? And then in null deflection position, all the current coming from this way will pass this way only. And if this length is say L, then this EMF E will be directly proportional to L. You know that no current is drawn from this cell. So it is an open circuit. So the potential difference is its EMF, right? Now what we do is we close this key. Now when this key is closed, this resistance will draw current from the cell, and it has some internal resistance R also along with it. Now in that case, the potential drop across this will be different. It will be lesser than E. So just look at it, the direction of the current drawn from the cell, from the driver battery, and see here. In that case, now see, when this key is closed, the potential difference across this this potential difference will be lesser than E, because this cell has got an internal resistance R, and some potential drop will be along this R also. So you know that V is equal to IR as well as V is equal to E minus IR. So now for this V, the balancing length will be lesser than in the previous case. See, now the balancing length will be lesser. Now we can find out L1 and L2, and then when we can make calculations. So let's see how we make calculations. So when key K is open, no current is drawn from the cell. So the potential difference is the EMF of the cell. And if the balancing length is L1, then we know that E is proportional to L1, right? Now when key is closed, current is drawn from the cell, and now the potential difference is reduced to V. Now if the balancing length is L2, then we know that V is proportional to L2. And from this equation and this equation, take the ratio, you get E upon V is equal to L1 upon L2. And you know the relation for internal resistance. R is equal to E upon V minus 1 into R. And E upon V is L1 upon L2. So putting this value here, we have got this relation for internal resistance of a cell. See, this one. Now we can experimentally we can find out L1, we can find out L2, and R is the resistance from the resistance box. So all these values are known, and we can find out the internal resistance of this primary cell. So these two applications you have to perform them in lab also. Now let us move to numerical problems, and first let us begin with meter bridge. Now here we have a meter bridge, and just look at this question first. Okay, find the unknown resistance X and current drawn from the battery when no current flows through the galvanometer. Read the question first. Here, find the unknown resistance X and current drawn from the battery when no current flows through the galvanometer. No current is passing through the galvanometer. That means this is a balanced Wheatstonebridge or a balanced meter bridge. You can see here we have 4 arms. This one, this one, this one, and this one. The lengths are also known to us. And what else is given? The resistance per unit length of the wire is 0.01 ohm per centimeter. That means ये जो मीटर ब्रिज की जो वायर है इसका रेसिस्टेंस पर सेंटीमीटर दिया हुआ है. आपको प्रैक्टिकल में लैब में रेसिस्टेंस पर सेंटीमीटर भी निकालना है यूजिंग दिस पोटेंशियोमीटर वायर ओनली. Okay, so let's see how we do it. Now, since no current is passing through the galvanometer, it is balanced Wheatstonebridge. So applying the condition, P upon Q is equal to R upon S. Now P is equal to X, Q is given to be 2 ohm. Now X की साइड में है 120 सेंटीमीटर, 2 के लिए है 80 सेंटीमीटर, and the ratio comes out to be 1.5, and then X is equal to 2 into 1.5 or 3 ohm. Just look at the previous diagram once again. See, look at it here. X upon 2 is equal to 120 upon 80. P upon Q is equal to R upon S. Okay, and you can see that the battery is of 4 volt. So I hope it's clear how we found out this value of X. It comes out to be 3 ohm, right? Now X and R are in series. You can see that in the previous case it was like this was X and this is R, right? And galvanometer is not counting now. We are just not counting galvanometer because there is no current passing through it. So this and this, they are in series. So X, their resultant Y is equal to 2 ohm plus 3 ohm, that is 5 ohm, right? And this X plus R is in parallel with the meter bridge wire. You see, if you let's get back to the previous diagram once again. See, when no current is passing through galvanometer, we can neglect this part. So X is equal to 3 ohm and R is equal to 2 ohm. They are in series, and this whole wire, they are in parallel. So we can calculate the equivalent resistance. Now, resistance of meter bridge wire is, the total length is 120 plus 80, 200 centimeter, or resistance per centimeter is 0.01. So 0.01 ohm per centimeter, और इसको मल्टीप्लाई करेंगे तो 2 ohm. तो रेसिस्टेंस वायर की, ए बी वायर की रेसिस्टेंस 2 ohm हो गई. So now this Y and Z, this and this, they are in parallel. So effective resistance will be equal to 2 into 5 upon 2 plus 5. You know that R1 R2 upon R1 plus R2, and you get 10 upon 7 ohm. Now we know the effective resistance in the circuit is 10 upon 7 ohm, and the battery is 4 volt. So I is equal to V upon R, and using this you can see that I is equal to V upon R, and putting the value of R here, we get 2.8 ampere, right? So it was a very simple problem based on meter bridge. Another problem based on meter bridge only. Just look at the problem first. In a meter bridge with R and S in the gaps, you have R and S in the gaps, the null point is found at 40 centimeter from A. That means just look at this A point also. See, the null point is found to be 40 centimeter from the end A. No, 40 centimeter from end A. Now, if a resistance of 30 ohm is connected in parallel with S, see, a 30 ohm is connected in parallel with S, the new null occurs at 50 centimeter. Now, clearly, when you add something in parallel, this resistance will change, and now the new null point is at 50 centimeter, right? You have to find out the value of R and S. आपको ये R और S की values निकालनी है, right? And to do that, we will be using conditions of balanced Wheatstone-Bridge in both the cases, because it is the meter bridge is based on this balanced Wheatstone-Bridge. So applying the condition for balanced Wheatstone-Bridge in the first case. What is happening here? The R upon S is equal to 40 upon 60, that is 2 upon 3. See, if the balancing length for R is 40, for S it is going to be 60. So that is 2 upon 3. Now after connecting 30 ohm resistance, R is same, no problem. But in place of S, we will have the parallel combination. And parallel combination, you know that resultant is R1, R2 upon R1 plus R2. So now we'll get S into 30 upon S plus 30 is equal to. Now the balancing length is 50 centimeter, and if it is 50 for R, it will be 50 for S, the other combination, parallel combination also, because the total length is 100 centimeter, 1 meter, and this is equal to 1, right? So from here, just cross multiply and you get R is equal to, take this whole thing to the right side, S into 30 upon S plus 30, that is 2 upon 3 S, right? And now from here, you can cross multiply, you can see things. So you can see 2S into 30. You see, look at it. We know that R upon S is equal to this R is equal to 2 upon 3S. R is equal to 2 upon 3S. So in place of R, I have placed 2 upon 3S, right? Now cross multiply and simplify. So when you cross multiply, you get this 2 into the denominator, S plus 30. This goes up here and this goes this way. So this is 30 into 3. Look at it. This S is cancelled on both the sides. So only 30 is left here. 30 into 3. I hope you understand it, right? So now from here, when you open the bracket, when you open this bracket, you get 2S plus 60 is equal to 90 and simplify karo 2s is equal to 30 or s is equal to 15 centimeter. We have found out the resistance s is equal to 15 centimeter, and you know that r is equal to 2 upon 3s from this relation. So this is 2 upon 3 into 15 and 3 5 times here, and this is 10 ohm. So s is equal to 15 centimeter and r is equal to, sorry, s is equal to 15 ohm and r is equal to 10 ohm. So in this way you can use this concept of balanced Wheatstonebridge to solve problems of meter bridge. And let us move to this problem of a potentiometer. Here, a cell of EMF 4 volt and of negligible internal resistance is connected in series with a potentiometer wire of length 4 meter. Now the EMF of the Leclanché cell is found to balance on 1.5 meter length of the potentiometer wire. Find the EMF of the Leclanché cell. Okay. So the driver battery is of 4 volt. That is given to you. You must understand this. This is your driver battery. So potential difference across potentiometer wire is 4 volt. And the length is 4 meter. The length of the wire is given to be 4 meter. Right. Now see, the internal resistance of this driver battery is negligible. That means all this potential difference across this potentiometer wire will be same as 4 volt and its length is given to be 4 meter. So we must find out the potential gradient. So the potential gradient is the potential, fall of potential upon length. Now the potential difference across the wire is 4 volt and its length is 4 meter. So potential gradient is 1 volt per meter. So once we know this, now the balancing length for Leclanché cell L is 1.5 meter. This is also given to you. So its EMF will be equal to K into L. Now the value of K you have just calculated, it is 1 and the balancing length is 1.5 meter. So you get E is equal to 1.5 volt. So EMF of the Leclanché cell is 1.5 volt. So the next problem, a very good problem. See here, in the figure, a long uniform potentiometer wire AB is having a constant potential gradient along its length. Constant potential gradient means the cell, this driver battery is giving constant current. Now the null points for two primary cells of EMF E1 and E2 connected in the manner shown as obtained at distance 120 centimeter and 30 centimeter. Now see, you have been given two cells. First they are connected in this way and the balancing length is 120 centimeter, and after this they are connected this way and now the balancing length is 300 सेंटीमीटर. तो ये उन्होंने 1 by 1 किया है ना. पहले सिचुएशन में देखिए, E1 and E2 are connected in opposite directions. See here, the positive terminal of E1 negative, for E2 this is negative and this is positive. So E1 and E2 are connected in opposite direction. So their resultant will be E1 minus E2, right? So जो पहली आपकी जो बैलेंसिंग लेंथ है 120 सेंटीमीटर वो E1 माइनस E2 के लिए है, और सेकंड केस में इन्हीं दोनों सेल्स को हमने सेम डायरेक्शन में ऐड कर दिया है. सो ऐड किया तो सी यू कैन सी प्लस माइनस दे आर सपोर्टिंग ईच अदर. तो सेकंड केस में EMF बढ़ गया तो बैलेंसिंग लेंथ भी बढ़ गई 300 सेंटीमीटर, राइट. सो वंस यू हैव अंडरस्टूड द प्रॉब्लम, नाउ लुक एट what things you have to find out. See, find E1 and E1 अपॉन E2, आपको E1 एंड E2 का रेशियो निकालना है, एंड पोजीशन ऑफ नल पॉइंट फॉर सेल E1. अगर हमारे पास सेल E1 अकेला जोड़ रखा है तब नल पॉइंट का पोजीशन क्या होगा, एंड हाउ इज द सेंसिटिविटी ऑफ द पोटेंशियोमीटर इंक्रीज्ड. इस पोटेंशियोमीटर की सेंसिटिविटी कैसे इंक्रीज करनी है. So we have to discuss these three things. So I hope the question is clear to you. Let us get into the solution. Let's see. See, in the first case, the cells are opposing each other. So you can see E1 minus E2 is proportional to 120 centimeter. In the second case, they are supporting. So E1 plus E2 is proportional to 300 centimeter. This is equation 1. This is equation 2. Taking ratio, we get E1 minus E2 upon E1 plus E2 is equal to 120 upon 300, and simplify कीजिए, you get 2 upon 5. Now cross multiply 5 into, they take 5 to this side and 2 to this side, and you get 5 E1 minus E2 is equal to 2 E1 plus E2, and then simplify it further, open the brackets, you get 3 E1 is equal to 7 E2, or E1 upon E2 is equal to 7 upon 3. The first part is solved, the ratio of E1 and E2. Now, the second part is to find out balancing length for E1. So, if the balancing length for E1 is say L1, then this E1 will be proportional to L1. We know that. Now, dividing this equation 1, this equation by this one. We can divide any of the equations, right? And then what do we get? We get E1 minus E2 upon E1 is equal to 120 upon L1. And just open this, you get E1 upon E1 will give you 1 minus E2 upon E1 is equal to 120 upon L1. And 1 minus, see we have just found out E1 upon E2, that is 7 upon 3. This is E2 upon E1, so 3 upon 7 is equal to 120 upon L1. And 1 minus 3 upon 7 will give you 4 upon 7. And then cross multiply and simplify, you get 120, L1 is equal to 120 into 7 upon 4, that is 210 centimeter. So the balancing length for cell E1 is 210 centimeter. अगर सेल E1 को अकेले जोड़ा होता तो balancing length 210 centimeter होगी. Now we have reached to the third part. How to increase the sensitivity of potentiometer. Now what do you mean by sensitivity first? Sensitivity means छोटे से छोटा potential difference भी नापना. And V is equal to KL, right? So if this K is small, this L will be large enough to be measured. L इतना लंबा होना चाहिए जो कि हमें आसानी से दिखाई दे. That means for the sensitivity, this K should be as small as possible. The potential gradient of the potentiometer should be as small as possible. और इस पोटेंशियल ग्रेडियंट को कम करने के लिए वी कैन इंक्रीज द लेंथ. व्हेन एल इंक्रीजेस, दिस रेशियो विल डिक्रीज एंड के विल ऑल्सो डिक्रीज. सो वी कैन इंक्रीज द सेंसिटिविटी ऑफ अ पोटेंशियोमीटर by increasing the length of its wire, that is by decreasing its potential gradient. It is a very important concept and you must remember. So another problem based on this potentiometer only, a very good conceptual problem. You see, in this given figure, this point A is balance point, X is point X is balance point. You have this driver battery P, this variable resistance R. See, अगर किसी resistance पर ऐसे arrow लगा दें तो ये variable हो जाता है. So variable resistance R. Now where will the balance point shift when R is increased keeping all other parameters unchanged. Now look at it once again. Look at this diagram. So this R is increased and all other things are constant. So when this R is increased, and you know that in case of balanced position, all the current is passing through this path only. No current passes through this path. Okay. So when this R is increased, this current I will decrease. And when this current decreases, the potential gradient will decrease, right? And when the potential gradient decreases, you see, this potential difference across this will decrease. Current I decreasing means potential difference decreasing, and potential difference decreasing means K is equal to V upon L. So when potential difference decreases, this potential gradient also decreases. This must be very clear. And if it is so, the balancing length V is equal to KL for any given balancing EMF. So if K decreases, clearly L increases, and in that case the balance point will shift towards the right side, or balancing length will increase, right? And coming to the second part, when S is increased, keeping all other parameters unchanged, you see. Now what we are doing is, only S is increased, this S is increased. But you know that during balanced position, no current is drawn from this cell. That means no current is passing through S. S से कोई करंट पास ही नहीं हो रही है, ये सेल Q ओपन सर्किट में है, तो जब करंट पास नहीं हो रही है तो ये इसको कम कर दें, ज़्यादा कर दें, कोई फ़र्क नहीं पड़ने वाला है. That means the balancing position is not affected at all, right? It is used, now then what is the use of it? It is used to control the current through galvanometer. Means when current passes through this galvanometer, जब ये बैलेंस में नहीं है तो गैल्वेनोमीटर से करंट भी पास होगा, उस करंट को कम रखने के लिए इस S को यूज़ करते हैं. Okay, so let's see how we give answer to these questions. So first part first, I have already explained. When R is increased, the current from battery P is decreased. This decreases the potential gradient K. So the balancing length Q, according to this relation V is equal to KL, will increase. So the balance point will shift to the right side. That is how you write in examination. Second part. Increasing S will not change the balancing position as no current is drawn from the cell in null deflection position. Null deflection. You must mention this point also. So these concepts are very, very important. So let us move on to the next problem. Again, a very good problem, and it is based on the internal resistance. So, in the following potentiometer circuit, AB is uniform wire of length 1 meter and resistance 10 ohm. Means from here to here it is 1 meter, the length is given, and resistance is given to be 10 ohm, right? Calculate the potential gradient along the wire and balancing length L. Now you know you have here a cell of 1.5 volt. Its internal resistance is 1.2 ohm. External resistance is 0.3 ohm. The driver battery is of 2 volt. And this resistance is 15 ohm, right? So in case of null deflection position, you see, the current is drawn from this driver battery, current will take this path, right? You see, so the current is passing through this 15 ohm resistance as well as this 10 ohm resistance. So this 10 ohm resistance from here till here and 15 ohm, they are in series. So the current drawn from the driver battery will be equal to 2 upon 15 plus this 10 series वाला, right? So हम निकाल सकते हैं current drawn from the battery. See, resistance of wire AB, RAB is 10 ohm. At balancing length, the current passing through AB will be equal to V upon R. Now V is 2 driver battery upon 15 plus 10, that is 2 upon 25 ampere. Now the potential gradient K will be equal to potential difference across AB upon length of AB. Now potential difference across AB is, this is I into R. Now I is 2 upon 25, we have just found out, and its resistance is 10, and upon length is given to be 1 meter, right? So using this, we get potential gradient as 20 upon 25 or 0.8 volt per meter. So the first job is completed. We have found out the potential gradient. Now, see, the cell is in closed circuit. If you look at it, the previous one, you see here. Even in balancing case, the current is drawn from the cell through this resistance. So here, the current, when we are talking about this, there is no current passing through this path. So that means this hole can be easily neglected. So you can see that the current in the circuit will be equal to this 1.5 upon 1.2 plus 0.3. They are in series. So now you can see the current drawn from the cell is E upon R plus R. E is given to be 1.5 volt upon external resistance is 0.5, internal resistance is 1.2, and you get 1 ampere. That means current drawn from the cell is 1 ampere. Potential difference across the cell, V, is equal to IR, and I is 1 ampere. So 1 into 0.3, that is 0.3 volt. So potential difference across the cell combination is 0.3 volt. Then its balancing length will be equal to V upon K. You see, V is equal to KL. So K is known to us. We can find out V upon, and V is also known to us. So V is 0.3 volt, K is 0.8. We have just found out, and simplifying it, we get 0.3 upon 8 meter, or convert it to centimeter. It comes out to be 37.5 centimeter. See, if you understand the basic concepts, you will not have any problem. And with this, I come to the end of this video. Thank you very much for watching this video.